Welcome to today's mathematical excursion. I'm your host, Ted Z. Before we tackle the infinite series in the thumbnail, let's look at a related one. 1 over k times k plus 1. So here I have taken p to be 1. Now let's consider the partial sums s big N. So we sum the terms from k is 1 to big N. So we have big N number of terms. Let's sum a few terms. The first partial sum, S1, so that's 1 over 1 times 2, and that's 1/2. Second partial sum, S2, oh, that's the previous partial sum plus the new term, so that's 2 times 3. So I work this algebra out, and I get 2/3. Likewise, the third partial sum, that's the last one, 2/3 plus 1 over 3 times 4. Okay, I work out this algebra, and I get 3 over 4. So from looking at this evidence, I can guess this. S sub n is n over n plus 1. This is just a guess, okay? However, we can make it more than just a guess. Okay, and I'll leave that to you to do. Prove this by induction. And now to find big S, which is the sum here, I take the limit as n goes to infinity of the partial sums S sub n, and okay, that's 1. So this thing here, this sum, S is 1. Okay. This is our main problem, like in the thumbnail, and p is some natural number. We know that this converges, so S exists. Why do we know that? Well, we know because we can compare it to series which we know do converge, like this one, 1 over n squared, n is 1 to infinity. Okay, so we know this has a sum. Now, what if we try guessing these partial sums like in part 1 of this video? Well, I've actually tried that and I didn't get very far. I mean, you can try it. It's kind of frustrating. So we want to take a more organized and logical approach. So what we will do is we will use partial fractions to simplify this. Let's look at this expression, p over k times k plus p. So it's like this one, but it's multiplied by p. And I can write this like this, k plus p minus k. Okay, so I add and subtract the k times k plus p. This is a really nice trick. And now I get this, and I can cancel out some stuff. Okay, this is pretty good because this kind of thing is much easier to deal with than this kind of thing. And so therefore I can express this now in terms of what I've just done. There. And this is very nice. This is kind of the key to making all of this work very nice. All right, so now we've got this and we're all excited. So it's really easy now to go off into the weeds and do some dubious things with infinite series. So let's see how we can go wrong. Okay, so far this is perfectly legitimate. I just replaced my inner expression, my terms, with this new way of writing each term. Okay, now here I've done something dubious. I've brought the summations inside. I've distributed them over this expression. So this involved rearranging this series. Now, here's my way of thinking about this. This term is positive, and this is absolutely convergent series because we know that this series, the original S series converges. This one converges, so we know this converges. So, okay, this is perfectly fine to rearrange these pairs. However, what we've done here is we've separated these pairs. Now we have a series using these two terms separately, and we're rearranging them. But this is no longer absolutely convergent. And not only that, like this is not even defined. This is divergent sum, and this is divergent. So what we have here is the difference of two divergent sums, or things. They're not even sums, they're divergent series that don't have sums. And so what does this even mean? I don't know. Oh, okay, it's possible to get the right answer by manipulating these series, and maybe there's a way to justify all these things. If you have some way of justifying this in the comments, you can tell me. But I want to avoid this. I don't like this kind of thing. And so let's get rid of dubious thinking, or dubious ideas like this, and we're going to use the tried and true method. And that tried and true method is to examine the partial sums of the series. So this is my nth partial sum, and it's quite convenient for me to take this p and bring it over to the other side. So that's what I'll do. And there, so we want to begin with this, and we'll study this thing, and then we'll take the limit as big N goes to infinity, and we'll have a nice rigorous proof. Great, so let's begin hacking away at this. Okay, S sub big N is our partial sum. And since we're going to be taking the limit as n becomes really big, well, it doesn't hurt us to make an assumption that n is bigger than, say, p plus 1. So let's say n is bigger than p plus 1. And this will help us to simplify things if we make this assumption. So here it is all expanded. Now, this is a finite sum. And because it's a finite sum, I can rearrange all these terms any way I like, and I don't have to worry. That's why it's so great to work with partial sums. So what I'm going to do is take these and move them all to the left. All right, so that's 1 over 1 plus 1 over 2 all the way up to 1 over n, this one here. And now I subtract off all the rest of this stuff. There, and now I get this. Now let's use this here. P plus 1 is less than n, so p plus 1 is less than n. This means that p and p plus 1 are somewhere in here. The pth and p plus 1th term are in here somewhere, so I have 1 over p and 1 over p plus 1 terms in here. And likewise here, n is greater than p plus 1. So in here, I can put a 1 over n term and a 1 over n plus 1 term. So obviously, okay, because of this, the nth term, this isn't the nth term, it's going to be bigger than this term here. Well, farther down the line, and it's got to be not as far as this term, because this is farther than the nth term. Okay, so you just have to sit back and think about this a little bit, but I'm going to write it carefully so you can see how these assumptions work. Okay, that's the first part, and because p plus 1 is less than n, this p plus 1th term here is not as far down the line as the nth term. Okay, that's one way to say it. There, and likewise for the nth term here and the n plus 1th terms, they're going to be in the middle here somewhere. And why did I do this? Well, now it's very clear that I can cancel out a lot of terms, and it's clear what I'm left with. So we see that, okay, let me use red for this. This cancels with this, and all this stuff up to the nth term cancels with all of this. So I have this harmonic sum, the pth harmonic number, minus now all of this. 1 over n plus 1 plus ... 1 over, well, I should put a plus here, 1 over n plus p. Okay, so I have a really nice expression for the partial sum. So let me write the whole thing down for you. Nth partial sum is 1 over p times all of that. Okay, and to find the actual sum of our series, that's the limit of the partial sums as n goes to infinity. Well, what do I get now? Well, I'm left with my 1 over p. This is the harmonic pth number, and that's minus 1 over p. Let's distribute that, but this is just 0 because the limit of this as n goes to infinity, this is not an infinite number of terms. This is p terms. It's only p terms, and each term gets smaller and smaller. As n goes to infinity, each term gets closer and closer to 0. So in the limit, this is 0. So I have finally proved it, 1 over p hp. And I did it without any screwy manipulations of series or writing down things that are dubious and possibly undefined and so on. HP is called the pth harmonic number. Okay, I will put together a playlist about harmonic numbers. I have a few videos about it. Now, I want to examine this question because computing harmonic numbers is not as simple as you think. You think, oh yeah, well, this is really easy. Look, it's just one over the reciprocals of numbers. I bet that's really easy to compute. It turns out it's not really that easy to compute, and I want to examine this question in the next part. Let's look at the troubles we can run into when estimating S or computing S for any P. We showed that S of P is 1 over P times the harmonic number HP. And this boils down to the difficulty of computing harmonic numbers. If they're easy to compute, then S is easy to compute. Turns out they're not that easy to compute. You may think they are. For example, this kind of sum, well, this is just a triangular number, p plus 1 over 2. That's easy. And so you might think, well, these harmonic numbers, they're pretty easy too. But, well, it turns out that there's no really easy way to compute them. Let me show you what I mean. Let's find S, P is 1. We plug everything in, we get 1. But we know that from part 1 of this video. If you do the same calculations for P is 2, you get 3/4. Okay, that's pretty easy. How about SP is 3? Do those calculations, get what? 11 over 18. Not so bad. How about P is 10? Well, that's 7,381 over 25,200. And already this is starting to get painful. Just for fun, what happens when P is 100? You get this enormous, massive rational number. And you see, if you don't have a special computer program to handle rational numbers, well, how are you going to compute these HPs? And how are you going to compute, finally, the SP? Right? So you say, well, surely there must be some simple way to compute HP. I mean, there's simple ways for many of these simple sums or series, right? Well, there isn't. HP is special. I looked around, and here's the best I could do. It's an asymptotic formula for HP. Let's see what it looks like. HP is log P plus gamma, the Euler-Mascheroni constant, plus 1 over 2p, minus all this stuff involving Bernoulli numbers. And Bernoulli numbers are not exactly easy to work with either. So what I'm going to do is just take one term of this and leave it at that. Okay, so I get this with 1 over 12p squared is my last term, and I'm going to ignore everything else. And recall Euler-Mascheroni constant is 0.577 and so on. See the playlist. All this stuff is related. Harmonic numbers, Euler-Mascheroni constant, log, all that stuff. Some beautiful analysis. So check out that playlist. Right, so here's our approximation function. Little s, that's a small s, is this function. And I'm claiming that this is going to be quite close to big S. So this approximates big S, P, especially when P is large, as we will see. Okay, let's try this out. Remember, S, P is 3. That's 11 over 18. Okay, and this is 0.61111, like that. Whereas little s of 3 is, hey, not bad. We've got at least a few digits right, so that's pretty good. Let's try some more. Oh, P is 10. That's 7,380, blah, blah, blah. We've seen that one before. That's equal to this. Okay, so let's try little s. Little s of 10. Little s of 10 gives us this. All right, so we see we got quite a few digits there. So this is good. Very nice approximation. I really love doing numerical stuff. I mean, what's the point of having a computer if you don't number crunch with it? So this stuff is very interesting to me, and I hope it is to you. And in the future, I would like to do videos about, let's say, Runge-Kutta method or numerical things, because it's so fascinating to play with numbers on a computer. It really is what a computer is there for. And if you're not doing number crunching with a computer, then you're not doing the right thing, my friend. Okay, let's do it. Let's do P is 100. SP 100, that was a huge fraction, so I'm not going to write that again. I'll give the floating point approximation for it. We get this 0.0518 and so on. And now let's find the little s approximation. Wow, that's very, very close. Let's see how far. Oh, wow, many, many decimal places. So it's really nice, really good. Okay, fantastic. Very, very nice. Well, I hope you liked this excursion into infinite series and harmonic numbers. Don't forget to like, comment, and subscribe. Tell me how much you like computing with numbers. Send me a super thanks if you really liked this video. And I will see you next time with more fascinating mathematics stuff.